Hi, this is a presentation of the flow simulation in an abdominal aortic aneurysm. We are Pedro Olvera, Narciso Martinez, and Alejandra Fierro, and we made up team number 10. First of all, it's necessary to define an abdominal aortic aneurysm. It is a permanent dilation of the abdominal aorta with a diameter of 3 centimeters or more. It often develops silently, but if it grows or ruptures, it can be life-threatening. It is the cause of the 1% of the deaths in men over 65 years old. Some of its risk factors are age, smoking, and hypertension, and some of the diagnosis methods are ultrasound, CT scan, and MRI.
Here we can see the mechanical properties of the abdominal aorta. With young modulus of 2.7 megapascals, Poisson's ratio of 0.45, yielding effort of zero point 0.5 megapascals, density of 2.0 grams over cubic centimeter. This data will be useful to fill in the characteristics of the material for the simulation in SolidWorks. On the other side, we have the mechanical properties for the blood, with density of 1003 kilograms over cubic meter and dynamic viscosity of 3.5 times 10 to the minus 3 power pascals per second. As well, this data will be useful to fill in the characteristics of the fluid for the simulation.
Now, a short description of the methodology. For the proper development of the simulations, it was necessary to use three different software programs. First, the segmentation of the abdominal aneurysm was performed with 3D Slicer. Then we used Mesh Mixer for error correction and mesh reduction. And finally, the simulation was run using the established parameters with SolidWorks.
After a thorough investigation, we declare all boundary conditions for pulsatil flow. These results represent the behavior of the velocity and pressure of an in vivo subject. This data was retrieved from a paper given by our professor.
Results are presented below. They indicate the pressure, shear stress, flow trajectories, and flow velocity of the abdominal aortic aneurysm at five specific time points of the simulation. These results were obtained using the previously established parameters.
The first measure takes place at zero point 0.3 seconds. We can see high values of pressure on the lower part of the arteria. Also, the maximum shear stress will be visualized in the lower part, having the lowest shear stress in the globe of the aneurysm. Finally, the flow velocity is stable on the higher and center part of the arteria, but on the lower part, the values increase because of the increasing of pressure. At zero point 0.4 seconds, the pressure will be very similar. The shear stress will have changes, having much more lower values. The flow trajectories will increase in volume of the fluid. The velocity will decrease, so we can infer that the fluid is stabilizing.
At zero point 0.5 seconds, the simulation reaches a point where pressure and flow are starting to present a negative tendency, leading to drastic changes on results, as shown on the images. When the simulation reaches zero point 0.8 seconds, all of the results are affected. This due to the decreasing pressure and flow velocity inside our model. Here we can observe some of the results on the shear stress, pressure, flow trajectories, and flow velocity and how they are decreased by this factor. At 1 second, the pressure and velocity decreases even more on the simulation, leading to a lower level of shear stress, pressure, flow trajectories, and velocity, as shown in the images.
After the results of the simulation, we can say that our study using 3D Slicer, Mesh Mixer, and SolidWorks allowed us to analyze the characteristics of blood flow and biomechanical forces in an abdominal aortic aneurysm. The results obtained revealed significant variations in pressure, shear stress, and blood flow at different time points. These findings have important clinical implications and contribute to a better understanding of this disease. Our work emphasized the importance of investigating and understanding hemodynamic conditions in abdominal aortic aneurysm to improve patient management and treatment. In conclusion, through the use of the different softwares, we conduct a comprehensive analysis of an abdominal aortic aneurysm, focusing on the mechanical properties and hemodynamic characteristics. This simulation allows us to gain insight of how an aneurysm evolves over time. The use of these softwares could hold significant clinical relevance in the field of vascular medicine. On the other hand, the technologies used on this project provide us with powerful tools to accurately segment and visualize the abdominal aortic aneurysm, enable a detailed investigation of its hemodynamics.